Hi, this video is an introduction to electromagnetic waves. In the previous unit, we discussed three different ways of heat transfer: conduction, convection, and radiation. And if you remember, we said that radiation is a way of heat transfer through space through waves, or with using waves. So what kind of waves are these electromagnetic waves? In your textbook, this is explained on page 533, and you have some nice pictures in there with good explanation. So I would advise that you also consult your textbook. But I've put some things on paper here to help those of you that have a hard time reading. An electromagnetic wave is a special type of wave. It actually consists of two different kinds of transverse waves. I have a picture of it here on the paper, and it's a tricky picture to kind of understand. You can see two waves in here. One of them represents the electrical field, and the other wave represents the magnetic field. And you can see that they are perpendicular to each other, so they sort of wave with respect to each other at 90-degree angle, like pages of a book. So if the spiral binding represents the direction in which the electromagnetic wave is traveling, then these two planes of the paper, this one and this one, they would represent the planes in which the electrical and magnetic field are vibrating or waving. Electrical and magnetic fields are both force fields. One of them is a force field in which electrical force can be felt by charged particle, and the other one is a magnetic field. We haven't discussed electricity or magnetism very much, so don't pay too much attention to that part. Just remember that there are two parts to the wave, an electrical part and a magnetic part, and they're perpendicular to each other. And it's hard to draw that in a two-dimensional picture, but if you look at the picture in your textbook, you should be able to understand how the electrical and magnetic wave are positioned to each other. And you should be able to reproduce this picture on the quiz to draw an electromagnetic wave. Okay, now electromagnetic waves are different from from waves like water waves or sound waves in one very special way, and that's that they don't need medium to travel through. Now they can travel through matter, they can travel through materials like glass, okay, or air or water. So they can travel through material things that have atoms in them, but they can also travel through an empty space, and no other wave can do that. A water wave needs water, right? Remember, waves are not very much, wave is not really what something is, it's more what something does, right? Now that doesn't apply to electromagnetic waves. Electromagnetic waves are actual sort of, to say, things, because they consist of waves in and out of themselves. So the electrical and magnetic field, as it can travel through empty space, and this is a hard concept to grasp, and it took scientists many years. They actually tried to go around this idea by trying to find some kind of an invisible substance that there is in emptiness of space, so that they could tell and justify that a wave can travel through that space. They never found that substance, and today we believe that electromagnetic waves can travel through empty space. So that's how they are very different from the types of waves that we discussed. And they are a transverse wave. So the magnetic and electrical field vibrate perpendicular to the direction in which they travel. Just as with the other types of waves, this equation about the speed, wavelength, and frequency applies, and you need to be able to use this equation to calculate either the speed or frequency or wavelength of an electromagnetic wave. The speed of electromagnetic waves is usually much larger than the speed of water waves or sound waves. In fact, electromagnetic waves are, in our everyday language, we call them light. So light, the speed of light is very large. And so if this value is large, then these two values, one of them or both of them, have to be large enough so that they multiply to this extremely large number. And the speed of light is different in different materials. and it is the largest in vacuum. All the materials through which light travel will slow down the light. So, for example, in vacuum, the speed of light is very close to 300 million meters per second. Now, that's an incredibly large speed. 300 million meters per second. That's many times around the whole planet Earth in 1 second that an electromagnetic wave can travel. You can imagine how difficult it is to measure these types of speeds. In your textbook, on the next page, on page I think 534, it explains some experiments that were early done to measure the speed of light. But just to help you with the reading of the equation, if the speed of light is 300 million meters per second, and let's say the light has a wavelength of 1 meter, so the length of the electromagnetic waves, if it was 1 meter, then the frequency would have to be 300 million hertz, or 300 million vibrations per second. That's a very large frequency, much larger than anything that you and I are doing in the world that we live in. We don't do anything 300 million times per second. And this high frequency has to do with the fact of what produces light, or what produces these electromagnetic waves. They are produced by vibrations of electrical charges, of electrons, protons, or any other particles that carry electrical charge. And these tiny elementary particles, they can vibrate at very, very large frequencies, and so these very large frequencies will produce very large frequencies of electromagnetic waves. Well, I think that's about it for now, and I'll see if I need to tell you something else. I'll upload another video.